So on this page, we are going to be looking at working with some redox reactions. So similar to what you saw when we put the zinc solid into nitric acid, there are a bunch of reactions that just don't work with the 6 main types. When you see those reactions, your goal is to get a little bit more comfortable with recognizing them. And in order to recognize them, the first thing that you should do is actually solve for the oxidizing and reducing species by looking at their oxidation numbers. So we're going to start that by finding the oxidation number of the chromiums in this half reaction. And notice that this is a half reaction because it's either going to be oxidation or it's going to be reduction. And if it's neither, it might be something like a double replacement reaction where nothing has actually occurred. And so if you're encountering a reaction in which the ions are actually staying the exact same as they were, so in this case the sodium ion is still a +2, the sulfate is still a -2, and the sodium is +1. The lithium is +1 and the chloride is -1, nothing has occurred to any of their oxidation numbers. So neither, it wouldn't make sense to actually write a half reaction at all. When you're looking at oxidation and reduction, we're going to start out and you solve for chromium ion. That's the easiest one since the charge will match its oxidation number. And then over here for the dichromate, we've got our oxygen, and oxygen, remember, is always -2. So since there are 7 of them, that's a -14. 2 chromiums added to that -14 needs to all add up to be the total charge of the ion. And the total charge of the ion is -2. That means with a little bit of algebra, we can see that this particular chromium is a +6. Since our chromium has gone down in oxidation number, that then tells us that we're looking at a reduction. And the reduction, remember, is of the atom itself. So in this case, it's actually of chromium atoms. There's also a definition of oxidizing agent and reducing agent. And an oxidizing agent is something that causes the oxidation of another reactant. That, however, means that the species itself is going to actually carry the atom that is being reduced. So in this case, the agent is always a reactant, and this particular reactant, being dichromate ions, carries the species that was reduced, chromium, and therefore, if it were mixed with another half reaction, the dichromate would actually cause the other reactant to be oxidized. That's why we call it an oxidizing agent. All right, as we look at silver, our next example, we're going to start out, we've got metallic silver, that's an oxidation number of 0, and then the silver ion, that's an oxidation number of 1. So in this case, our oxidation number has gone up. And that means that we have the oxidation, and this is the oxidation of elemental silver and the silver atoms. Just like an oxidizing agent, we also have reducing agents. Reducing agents are defined as species that carry the oxidized atom but are in fact causing the reduction of something else. So in our case, this is the elemental silver that's acting as the reducing agent. Okay. Your lab is meant to show you how to work with activity series. And in your lab manual, you will see that there is an activity series. In that activity series, it's actually comparing just metals. Your activity series is going to be mainly looking at reductions. So what does the metal look like? Oops, oh dear, sorry. What does the metal look like as you are working with it? And so in our case, we would be looking at the metal ions gaining electrons. And in this case, we'd actually be looking at 2 electrons being gained, since I wrote a metal ion that was positive 2, turning into a metal. So in your lab, and this is experiment 11, what you will see is that you should have reacted a whole series of metals with other metal ions. So let's write another metal. Being reduced. And notice we can tell that it's being reduced because both of these reactions have electrons that are reactants, which means that they're in fact being gained by the metallic ion. If you are able to react this metal here as an ion to this metal as a solid, then what you'll have is, instead of these individual half reactions, you'll actually be showing that the first metal, M plus 2, and the solid, letter N, can react together. In the activity series, what you're really saying then is that this metal with the ion is being reduced. And since it's being reduced, it's actually causing the oxidation of this other metal, letter N. When that happens, we can line up the ability for the metallic ions and the metal as solids as to whether or not they can be oxidized to become cations, which in this case N can, or if they really couldn't. So if we did this reaction the other way, mainly saying that we took the N as an ion and reacted it with the metal M as a solid, we would not be able to see a reaction. Being able to predict whether an ion can cause the oxidation of a solid metal is what the activity series is for. And so when you look at the activity series, you're going to see that it's going to list off a number of metals at the top, and it's going to be listing them as solids. So lithium is up at the top, sodium is up at the top, and those are metals that can be easily converted into ions. And if they're easily converted into ions, they're going to be oxidized easily. So they can react with water, they could react with acids, they could react with air even. And as you get lower, you're going to find other metals like gold, for instance, or platinum. At that point, those metals have a really hard time oxidizing. So they do not want to be turned into any sort of ion. They would much rather stay in their metal form. And so in experiment 11, you're trying to decipher which metals are more likely to be oxidized, which would mean those are solids that are more likely to turn into ions, versus which other metals are less likely to be oxidized, meaning they would much rather stay as a solid. In our example over here on our left-hand side, the metals at the top would be representing that metal N that I wrote, where they're easily oxidized. The metals at the bottom would be more likely to represent the letter M as a metal because they're less likely to be oxidized. So you're going to line up the metals, and then just to give you a sense of how the reactions actually go, we've mixed in the halogens versus the halides. And of course, being nonmetals, you're going to see that they're going to have similar characteristics, but opposite in terms of their reactivity, because they're going to be gaining electrons as halogens. Okay, next up, and this, I have a worksheet for you. That worksheet is going to be, it's going to be numbered 3, because it's sort of the third one in the series. You're you're going to be looking in your lab manual, and when you look in your lab manual, you are going to find a page that has common oxidation and reducing agents. When you go into that lab manual, then it should look like, I did not save it apparently, so hold on. Okay, so it should look like this. Oops. And let's just zoom in a little bit. If you take a look at this, what you are going to see is that 1, I accidentally drew a line on it, and that 2, we have a division going right down the center, where over on the left-hand side, we have common oxidizing agents. These are all carrying a species that is going to be reduced. And on the right side are the products that they would turn into. So if I found this permanganate ion, for example, in an acidic solution, I would create this manganese ion, so Mn+2, as product. That's because we're going from a +7 on the permanganate. You might remember doing that in the notes. And now we're turning it into a +2. So we're reducing the oxidation number, and therefore we're looking at those as species. This is the reaction that you saw in the demonstration, where you had HNO3 and it was turning into nitrogen dioxide. You also see that there are some halogens. We've generalized those halogens as an X instead of listing them all off. Remember that it's referring to F2, Cl2, Br2, I2. And their halides are their negative ions, so F-, Cl-, Br-, and I-. We also have here metallic ions, so for example, an iron 3, right, would be ferric, and it could be converted easily to iron 2, ferrous. And so again, notice that that's also a reduction in oxidation number. On the right half of the table are common reducing agents, and those are species that are going to be actually carrying something that is oxidized. So you can see that our very first one is, again, a halogen series where our halide is turning into the halogen. We also have ones where our halogen could turn into the hypohalite, or the halogen could turn into the halate. You have metals turning into metallic ions, and then of course some of these others. The table can be read in 2 directions, and that's typically going from left to right, but you can also turn it around and go from right to left. So if you found CO2, it is, I suppose, possible that you could, instead of oxidizing, you could reduce the CO2 into oxalic acid. Same idea here on the other side. Typically, you're going to be reading it left to right, but you might be able to force a reaction that goes right to left. So if we were to take a look at our zinc solid that we did with the demo, and we reacted it with the nitric acid, we would see that because Mr. Sio and I were using the concentrated version, that nitric acid turned immediately into the nitrogen dioxide, which was that brown gas. As you guys stated in class, that zinc is actually going to be joining up with any leftover nitrates that might be present. Oops, there we go. And then really, you may be wondering what happened to that hydrogen. We clearly didn't try to ignite it. I wasn't going to stick my hand in there with a burning match and poison myself off. But it does turn into another chemical, and that's water. And so we have water as a liquid. And if you look on your solubility table, you can see that the zinc nitrate, being ionic as well as highly soluble, is in fact going to be soluble. And therefore, we would write this looking first at this molecular formula, and now looking at our net ionic reaction, our concentrated nitric acid would be separated into ions. We would be creating the nitrogen dioxide as a gas. The zinc ions are what we're interested in. And we're going to leave off this nitrate because part of it, right, some of the nitrate ions are in fact going to be spectators, and some of those nitrate ions are going to be used to create the nitrogen dioxide. So since some of them will be spectators, these ones here, which are unimportant to our products, are going to be left off. And then our water, of course, would be present. So now we can see the zinc is being oxidized. And we can also see the nitrogen is being reduced. In addition, you can find this series up above. So if you look at your nitric acid right here, turning into the nitrogen dioxide, and then also you can see the metal, that would be our zinc, turning into the metal ion, the zinc plus 2. All right, so we're now back on our notes page, and what we're going to be looking for is basically trying to make some predictions of what's occurring as products. These are not really going to be following any of the 6 main types of reactions, and you're definitely not going to get a Bronsted reaction where a proton has been shifting. You do want to look for one species that is definitely being reduced and one species that is being oxidized. For all of the reactions that Mr. Sire and I have selected, we have not selected anything that would have multiple reductions or multiple oxidations. It's also very smart to notice your strong electrolytes, similar to your strong electrolytes in the Bronsted reactions or hydrolysis. They tend to be the ones that are going to be removed. And really watch for those metallic ions because they're going to be doing quite a bit of work in these redox reactions. So, first thing you want to notice is that we have a solution of acidified. The word acidified almost always indicates that it is going to be a redox reaction. It also means that you're going to be taking some hydrogen ions, right, because that's the acid. And if you watch the video on balancing, of course those hydrogen ions are the extras, right? They're the ions that are present to help with the balancing. Since I know it's going to be a redox because of the word acidified, I'm going to go ahead and write my ions instead of my molecular equation. It'll make it a little bit easier as we look at the common oxidizing and reducing agents table to identify what's actually occurring. So here's our potassium permanganate, and here is our sodium bromide. All right. Now, right off the bat, because of balancing, I know that I can immediately write water on the other side of the reaction to go along with my hydrogen ions. Again, we're not balancing these reactions. We just know that if you're partnering an acidified solution in the redox reaction, you need to partner that ion with the water molecule. Now we're going to go back over and we're going to look at our table. And as you look at your table, the first thing you want to notice is there is your permanganate. Since our permanganate is listed first and it's in an acid solution, we know that manganese ions are going to be one of our products. We also know, because it was listed, permanganate that is, was listed as a common oxidizing agent, that the manganese is the species that is being reduced. And since that's the species being reduced, we now need to look on the other side of the table to see if we can identify something that could be oxidized. If you remember, we had bromide, and there's the bromide ion. It's written sort of in secret as a halide. But notice it's going to be turning into a halogen. So that is going to be our second product. So bromine, Br2, is our second product. And that, of course, being from the right side of that table tells you that your bromide was going from -1 down to a 0, and so that, I'm sorry, up to a 0. So that means that you're actually looking at a lovely oxidation. So following our rules, you have to have a reduction and you have to have an oxidation. We have one of each. You also want to start to look at your strong electrolytes, and they tend to not react. So our strong electrolyte potassium ions and sodium ions, those are going to be our spectators. All right, let's look at the second one. We have solutions of tin 4 chloride and ferrous chloride. One of the things you might notice is that as you get more and more comfortable with your solubility table, chlorides are highly soluble. And you also might notice that if we tried to do a double replacement reaction, we'd just be putting tin back with a chloride, and we'd be putting iron back with a chloride. So if they're already soluble and they're just really going to flip positions, we know that a double replacement reaction is really not possible. So again, let's take a look and write out our ions. There's our tin 4 chloride, and here's our ferrous chloride. And now we want to remember metallic ions are really common. They're great components for doing work. If the chloride ion had been doing work, it would have already done the work with the tin or done the work with the iron. So you can already tell that that's going to really fall into our strong electrolyte category and be something that we'll be spectating, and we can get rid of it right now. If you're not comfortable getting rid of it right now, we can do it later, but I'm already crossing it out, so there you go. Let's look at our table then. So you go back into your lab manual and you take a look at this table, and we see this one, our metallic to metalless ions. As you look at this, again, remember what a perfect example of taking your ick species to us, and then swinging around and using the table from right to left, taking your us species to ick. Let's take a look at that reaction then. We have a stannic, that's our tin 4, so it could go down in oxidation number. Notice our reduction right there. And then our ferrous could go to ferric, and that would be going up in oxidation number, meaning that now we have our oxidation. So here again is our reduction. Here is our oxidation. And now we've covered the fact that we needed one reduction and one oxidation, and that reaction is done. All right, our last one is a solution of oxalic acid added to an iron 3 nitrate solution. This one's going to be a little harder to recognize as a redox reaction because you might, see perhaps iron 3 and oxalate might go together. Right now, however, it is in this area where we know it's redox, so I'm going to go ahead and split it into the ions. You might be asking yourself why it is that I wrote that oxalic acid as a species, one enormous molecule, even though I did tell you in the directions it was a solution. But again, remember that is a weak species. So because it is covalent and it is a weak acid, remember not to dissociate it. The iron 3 nitrate, of course, can be dissociated. Okay, once you have your reactants present, you're going to head back over to your table. And as we look at our table, we see, here is the oxalic acid, acting as a reducing agent, which means the carbon is being oxidized. It's being oxidized into CO2. So let's jot that down. And again, we know that that is now our oxidation. Since that is our oxidation, we now want to jump into our table one more time, and now we're looking for a reduction. So since that came from, the oxalic acid came from our right side, hopefully we can find something over here on our left side. We have some great species here, and let's just double check. We do have, I believe it was iron 3, and if that's the case, iron 3 is a metallic. We can bring it on down to the metalless state. So we're going to go ahead and we're going to do that. That is now going to give us our reduction. And you might be able to guess at this point who is going to be removed as a spectator ion. If you said nitrate, you are correct. And then you might be wondering, if we're looking at carbons and oxygens and irons on our left, we have carbons, oxygens, and irons on our right, what happened to those hydrogens? Hopefully you're getting the gist that in terms of balancing, those hydrogens are going to act as hydrogen ions, even though our species is weak and we're not writing it as ions. Because of that, we are going to have some water molecules over there on the right-hand side. It is really important to keep in mind that hydrogen, ion, and water molecule. It's important on the AP test. It helps you balance, so you do want to kind of keep those in mind. Okay? And that's all for the notes. And again, we'll have that worksheet for you so that you can